Next, I'd like to talk about a couple of special cases. When your rigid body is subject to only two forces, any kind of forces, reactions and applied force, okay, total forces are only two. Okay. It's called a two-force body in equilibrium. Okay. So it's a two-force system. The second special case is when this rigid body is subject to three forces. Now, these two special cases, okay, according to what we learned so far, okay, the forces must behave a certain way, okay, in order for the rigid body to be in equilibrium. First, look at the two-force body. Let's say this body goes like this. Okay, the free body diagram, okay, for this rigid body, right, just draw the two forces, right? But because of the fact that the forces, sum of forces might equal to 0, okay, and also the sum of moment about any point, okay, also must equal to 0. This implies that these two forces applying on this rigid body must be acting along the same line of action. Okay? Just so that for this first equation, this force cancels out this force. Okay? So that's the only way that this equation satisfies. Also, okay, this equation being satisfied as well, because okay, if you take moment about, let's say, any point along this line of action, okay, then none of these forces will have any moment at all. So therefore, some moment equals 0. But if, let's say, point O is right here, okay, some moment about point O equals 0 due to these two forces, okay, and keep in mind, some moment equals, in terms of the scalar, okay, the magnitude, moment equals force times d. That's the shortest distance, the perpendicular distance, okay, between point O and the line of action of force. So this is d. Okay, so this force on the left will create a moment F1 times d. That's counterclockwise. So the second force will create exactly F1 times d also, but clockwise. Therefore, some moment about point O equals 0. They cancel out. So this is the only way where this rigid body can be in equilibrium, if it's subject to only two forces. Okay, they have to be along the same line of action. If it's subject to three forces, there are two possibilities. The first is like this. F1, F2, and F3 must be concurrent, which means that the line of action of these three forces must meet at the same point. Okay? Concurrent. Or, if two of them are parallel, then the third must also be parallel, okay, to the other two, like this. Okay? So these are the only ways where these two equations are satisfied, okay, for the rigid body to be in equilibrium. Okay, let's look at example 5.13 in the textbook. And we have this lever right here. Okay, it consists of two pieces, right? This A, B, C, okay, and then another piece, okay, B and D. Okay, that's linked up to it this way. Okay, now point D and point A are all pivoted, okay, and they're free to rotate. And you're asked to find the reaction force at A. Okay. So in this problem, there are a couple ways to analyze it. Now, RAX and RAY are the unknown. Okay. So we want to choose a free body diagram that will allow us to find the reaction forces here, right? So we can split this whole system up into two pieces. Okay? And the advantage is looking at just this BD piece, right? So just take this out. Okay? So this piece is subject to only two forces. A force at B, okay? It's a reaction force, right, at B, and then a reaction force at D. Okay? That's it, nothing else. In this problem, we're ignoring the weight of each piece. Okay? So this is a two-force body, which means that these forces must be acting along the same line of action, and then they must have the same magnitude. Okay? If this is 100 pounds, then this must be also 100 pounds. Okay? Just an assumption, right? So we have to actually go ahead and calculate that. Okay, so knowing that these two forces must act along the same line of action, then you know exactly how they are pointing, because you know that this is 0.2 meters wide and 0.2 meters long. So this triangle right here is a 45-degree triangle. Right? It's a right triangle. Right? So this force is acting 45 degrees. Okay. Moving on to this ABC piece right here. So you have this applied force, 400. You have this force, exactly this right here. Okay. Except that this, okay, is the force exerted by this ABC piece on this BD body. Okay. And this force is the same as this force in terms of magnitude, but they're opposite, because this force now is the force exerted by BD on ABC. Okay? So that's point B, that's also point B. Okay? That's C to A. So these two are the opposite. Okay? Also, look at this right here. This piece ABC has the third force. That's exactly the reaction force. Okay? Now, there's a couple of ways to draw the reaction forces. You can draw the components, RAX and RAY, and that's fine. Or you can just draw RA itself. Okay? These two are actually RA vector. Right? So, I can just draw that one single vector. Okay? RA, okay, pointing in some direction. Right? But what direction? Do I know that? Well, some direction. And look at this right here. There's no other force acting on this rigid body ABC. So, this is actually a three-force body. A three-force body must satisfy one of these two conditions. Right? And since this 400 Newton and this F right here, the reaction force, are not parallel, this means that it's the first case right here. So which means that this third force must be pointing in a direction so that these three forces are concurrent. Okay. So I'm going to extend these two lines right here where the join is exactly where the third force, this RA, is pointing. Okay? So that's how I figure out the direction of this RA. Okay. So, so now we have these three forces, and we know exactly how they're oriented. Okay? And they'll meet at this point O right here. We have this unknown force F, and we have this other unknown force RA. And there are two forces, two unknowns. Okay? Two unknowns, we can easily come up with two equations, right, for this whole system. Right? Let's do a sum of forces. That's all. Okay? So just solve for F and solve for RA. And that's all. Okay? So F, you know, is 45 degrees, right? What about RA? Well, knowing that where it's oriented, well, then you can just use geometry to help you figure out the angle. Right? this angle theta right here. Okay, so knowing what's given here, so let's try to figure it out. Let's say, look at this triangle right here. Okay, so this triangle. And so from this point A to O, which is up here, so the vertical distance is 0.5 plus 0.2, so that's 0.7 meters. And then this distance, see, if this is 45-degree angle, so this is 45-degree angle also, right? Okay, and you know that from here to here, it's 0.5. It also means that this is 0.5. Okay, because look at this triangle right here. Okay, so knowing that this is 0.5 and knowing that this is 0.1, so you know that this is 0.4. Okay, so this triangle right here, and knowing the two sides, you can find the angle. This is the right triangle, right? So just use tangent, right? Equals opposite over adjacent. So theta equals arctangent 0.7 over 0.4 roughly equals to 60.3 degrees. Okay, so knowing this theta, then the rest is just piece of cake, right? So you know this angle, right? For this force, you know this angle for this RA. Two unknowns, two equations. Right? The math is just very straightforward. Okay, alternatively, you can solve for this problem by, let's say, drawing the components of RAX and RAY. Okay? So you have this force, the given force 400, and then this is the reaction force, and then now I have RAX, RAY. In this case, then you don't have to try to figure out the angle here, right? Because it's just horizontal or vertical. Okay, but now I have three unknowns instead of two unknowns, so I need three equations. Well, we do have three equations, don't we? And we also have some moment equation. Okay? A moment about some point. Just choose any point. Well, choose a good point. And the good point is where a lot of forces pass through that point. Well, look at this right here. I have these two reaction forces passing through point A, so I just choose point A because they don't create any moment about point A itself. Okay, so this way, three unknowns, three equations, no problem. Okay, and there's also a third free body diagram you can draw to analyze this problem. Okay, I can draw ABC and BD together. Combine them as a single free body diagram. Okay, so a single piece. What happens here now? What happens here is, well, if you look at the last video, we talked about internal versus external forces. This force F at point B and this force F at this point B, they're equal but opposite. We combine the two, they become internal force. So they disappear. Okay? So there's no force here now because it becomes internal. So the only force or forces that exist are are these two, but also a reaction force here, which is this F right here.